At D2I, what we're looking at is trying to help scientists manage their data through metadata. We're trying to make sure they get the maximum scientific value out of their data. And this data could come in a number of forms. It could be in observations that they've done. It could be from long-running workflows, long-term experiments. It could even be from long-term studies. And what we're trying to do is say, here's all this valuable scientific data. There's a deluge of it coming out now. But scientists can't find value. This data is stuck inside files, and if they can just get the data that they need, they'll get some scientific insight. And one thing we've developed in D2I, it's called XMC Cat. It's for managing data through metadata. And metadata is, you've probably heard, is data about data. And we developed it in the context of LEAD, which is atmospheric scientists, but we're also now applying it to an astronomy project for a large telescope that's going into production in a couple of years. And we're also looking at it with some ecological data where they're trying to manage data they've collected over a couple of decades in a legacy database. And we're looking at putting XMC Cat in front as a way that scientists can query that data. So a couple of features of XMC Cat that are valuable to the scientific community are that each community sort of develops its own metadata schema. And there's some standards out there, but what we're trying to do is adapt to the community. So instead of having each scientist or each community adapt to us, we adapt to them. So here we're looking at a fragment of the LEAD schema, which is based off the FGDC standard for geospatial metadata. And each community has a schema that they've developed. Some build off of a standard like the FGDC, like we did. And what we've done is with XMC Cat, we come through and we identify what are the concepts within that schema. Here we've drawn a line through that. And this identifies what elements in the schema identify a concept particular to that domain. We partition the schema on these concepts. Once we've done that, what it allows us to do is set a global order at that level, at the concept level, and at a higher level in the schema. And this is important for when we go to rebuild results. It allows us to do it very quickly. As the data is coming in, then the first thing we do is we parse it into these concepts, and we store what's known as a character large object, or CLOB. We store a chunk of XML for each of those concepts in the database. We push all of the namespaces down, so each CLOB that's in there contains everything it needs. What we also do is we take the leaf elements and we shred that metadata. We're parsing it apart and we're storing each of those leaf elements in the database as a very strongly typed data based on their data type. And that's bringing those elements into the database. And what the user does then is they come along and they query over that shredded metadata. So when we talked about the interface that adapts to the schema, what we're doing here is they come in and they can query over those concepts in their schema. They can query over any of that shredded metadata. That identifies what objects match their query, and then they can take those CLOBs very quickly because of that global order, grab all those CLOBs and rebuild a query result that then comes back to the user based on their community schema. So this allows us to do very detailed queries without being tightly tied to the community schema, but still being able to communicate in that community schema. We really hope that scientists will contact us and let us know what their metadata needs are. They can reach us either through our website or give us a call.